Dear ladies and gentlemen, welcome to my presentation about fire design methods for timber floor elements, the contribution of screed floor toppings to the fire resistance. My name is Michael Rauch and I'm a research associate at the Chair of Timber Structures and Building Construction at the Technical University of Munich. The motivation for this project comes from the existing requirements for ceilings in Germany. We have the requirements for the fire resistance, such as REI 30, REI 60, or REI 90. And these requirements have to be fulfilled for wall and floor elements, and both have to be classified from both sides if they are used as separating elements. Currently, there exists no possibility to consider screeds as fire protecting layers in any calculation method. Only tabulated data offer the possibility to consider these layers on the upper side of ceilings. So the idea was to develop a calculation model to consider the contribution of screeds and noise insulation to the fire resistance in future. The basis for the calculation model is the structural fire design of ceilings according to the current draft of the EN 1995-1-2. There are two calculation models, one for the load-bearing capacity, which is based on the charring of timber, for example, the stub for timber frame assemblies or for CLT elements. And for the integrity or isolation, there exists a calculation model based on the separating function method, which is a layer by layer calculation method. You can see it on the right. For all the layers in the construction, we calculate a protection time with a temperature criteria of 250 Kelvin. And for the last layer, we calculate insulation time with a temperature criteria of 140 Kelvin in the middle and 180 Kelvin at 1 point, maximum temperature increase. The sum of these times leads to the insulation time of the whole element. And this separating function method offers the opportunity to add new additional materials to calculate the fire resistance of elements or the start of charring after protecting layers. So the implementation of screeds as protecting layers for ceilings is possible in this method. But no values for cementous screeds could be found in the literature, which can be used for these calculation models. So far, the first step of the study was to do some small-scale tests to measure the heat transfer and the temperature profile behind the layer of screed and noise insulation. Based on this test input parameters, for the numerical simulation could be derived, and some parameter studies were done. This is the basic to evaluate analytical equations to extend the separating function method of the EN 1995-1-2. The heat transfer through the screeds was measured in a fire test according to the German DIN 4102-8. The temperature in the furnace was measured by plate thermocouples according to the EN 1363. You can see it here on the right picture. And the furnace where we did the tests, you can see here in this picture. And in this picture, you can see the specimen with a dimension of 50 by 50 centimeters, where the heat transfer was measured. The test specimen were mounted vertically because of the geometry of the furnace. This configuration is more conservative compared to the horizontal construction. To avoid the fall off, the screed layers were fixed by screws. Different thicknesses and backing materials, such as particle board or mineral wool insulation, were tested. The diagram on the left side shows the result of test 1 until test 4. For the protection time, the temperature of 270 degrees is evaluated and shown in the diagram for the different screeds and different thicknesses backed by a particle board. Test 1, 2, and 3 was done with a cementous screed, and test 4 with a calcium sulfate screed. You can see that the calcium sulfate screed with a thickness of 35 millimeters has a protection time of 45 minutes compared to a cementous screeds with a thickness of 35 millimeters, which has a protection time of 30 minutes. You can also see the horizontal plateau of the calcium sulfate screed where the water of the gypsum evaporates. This leads to the longer time for reaching the 270-degree criteria. All screeds in this test series were directly exposed by the fire and were backed by a particle board. In this diagram on the right, you can see test number 5 and 6, where the screeds were backed by a stone wool with a thickness of 15 millimeters. This shows the influence of the backing material. For example, for the screed with a thickness of 35 millimeters, the temperature of 270 degrees was reached 4 minutes earlier than compared to a backing material of a particle board. And in the next diagram, you can see test number 7 and 8. There, the stone wool was directly exposed to the fire and the screed was used as backing material. This shows a positive effect of the screed as a backing material and compared to the particle board as a backing material. To do numerical simulations, material parameters for screeds are necessary. Starting from the material parameters for concrete, according to EN 1992-1-2, the material parameters were calibrated based on test number 1. You can see it here in this diagram. The multi-objective genetic algorithm integrated in ANSYS was used to optimize the material parameters for screeds based on the response surface method. Here you can see the response surface for the temperature evaluated at 1,800 seconds. The correlation of parameters show which parameters are relevant and which can be neglected for this optimization process. Based on these results, the thermal conductivity of concrete was used and the specific heat capacity of concrete was optimized to be used as an effective parameter for the screeds. The results of the numerical simulation compared to the fire tests with different thicknesses show a good accordance. You can see the results in the diagram on the right. The blue lines are the results of the simulation and the black lines are the fire tests. The optimized material parameters for screeds under isofire, which are proposed, are shown in the full paper. Based on the parametric study, the equations for the separating function method were introduced. These equations are presented in the diagram on the right. You can see it here for cementous screeds, and you can see it here for calcium sulfate screeds. Additionally, position coefficients and the K2 values to extend the separating function method were developed and are presented in the full paper. These equations offer the possibility to consider screeds in the separating function method or to calculate the start time of churn behind floor constructions with fire exposure from above. For the ease of use, different floor constructions were calculated and are presented in the table on the right. For example, for Screed itself, the time reaching 270 degrees of a Screed on a wooden substructure is shown in line 1. There you can see that a Screed thickness of 35 mm is enough to reach a protection time of 30 minutes. For a protection time of 90 minutes, a Screed thickness of 80 mm is necessary. If you have sound insulation under the Screed, for example, here you can see that for 90 minutes protection time, a Screed thickness of 60 mm is enough, combined with this 15 mm sound insulation. The protective effect of Screeds after reaching the temperature criteria of 270 degrees is considered by the K2 factor. The positive effect of the lack of oxygen is neglected in the calculation model. And so the K2 value represents a conservative result. These assumptions done in the study lead to a conservative model compared to the test results. In practice, many questions relate to the construction principles. If the Screed is considered to calculate the fire resistance, all edge and movement joints have to be filled with non-combustible mineral wool with a melting point for more than 1000 degrees Celsius according to the German DIN 4102-4. In the opinion of the authors, the effect of the water-filled pipes of the floor heatings could be neglected, but these constructions were not part of this investigation. The summary and the outlook. The thermal material properties can be used for further numerical investigations in future. The equations of the study extend the current separating function method in the draft of the Eurocode, and Screeds can be used as an additional layer in the method. So it is possible in future to calculate the ceilings, for example, from above. For practical use, typical floor topics were summarized as tabulated data as shown in the slide before. For German requirements from the upper side, the gap of missing data for Screeds and noise insulation as individual layers could be closed with this investigation. Thank you for your attention, and I look forward to the discussion.